Chapter 9.6 is our last test for divergence or convergence, and it's called the ratio test. So if we have a series whose terms can be called a sub n, then when we look at the limit of sort of the next term over the previous term, so we're looking at the ratio, the absolute value, so we're looking at the magnitude here of the one term and the term after. So we're looking at a sub n plus 1 over a sub n, and we're looking at that ratio as the value of n approaches infinity. If that ratio, if the limit of that ratio is less than 1, then our series is going to converge. If the limit of that ratio as n approaches infinity is greater than 1, then that series is going to diverge. Right? If we get a limit that's equal to 1, then the ratio test is inconclusive. We need to find some other test. All right? This test works very well with problems that involve factorial, because this ratio will frequently allow us to cancel out a lot of those factorial terms and give us something that we can actually find the limit of. So an example here, we're looking at 2 to the n over n factorial. All right, so when we set up this limit, this ratio, we want to take the original a sub n, and that's the denominator. So that has to be in the denominator. And then in the numerator, we're just going to increment n by 1. So here I have n, here I have n plus 1. Here I have n, here I have n plus 1. Notice that the n plus 1 is in parentheses, and then we apply the factorial. All right, so we have one term and the next term after that one that we just looked at down here, and we're looking at the ratio of those and the magnitude of that ratio as n approaches infinity. So here we're dividing by 2 to the n over n factorial, so that's really, we are multiplying by the reciprocal. And you can see the nice thing about this is when we do this, not only does the 2 to the n cancel out and we're just left with the 2, but this factorial also cancels out. So remember, this is n plus 1 times n minus 1 times n minus 2 times n minus 3, etc. This is n times n minus 1 times n minus 2 times n minus 3. So everything other than the n plus 1 cancels out, and we're just left with a real easy limit, and that limit obviously approaches equals 0 as n approaches infinity. So 0 is less than 1, therefore this series is going to converge. And of course we have to justify it. We have to say it converges by the ratio test. All right. The next example here is an n plus 1 factorial over 3 to the n. So that's going to be our denominator in the ratio that we look at. And now instead of n plus 1, the numerator is going to have n plus 2. So we increment it by 1. And then 3 to the n, and then in the numerator here becomes 3 to the n plus 1. And then a really similar thing happens. We multiply by the reciprocal. So the n plus 1 cancels out all this stuff here other than the n plus 2. So that's all that's left. And the 3 to the n plus 1 and the 3 to the n cancel out everything but a 3. Now we can look at that limit. This limit, the numerator is going to approach infinity, so the limit itself is infinity. That's obviously greater than 1. So this series is going to diverge by the ratio test. Right? In these examples, we had one of our limits was equal to 0, and one of them was equal to infinity. That's not always going to be the case, nor is it necessary for it to be the case. So we could get a finite limit. So we could get a limit of 2 or 3 or 1.5, and those would all have indicate a diverging series by the ratio test. Right? Whereas if we had some fraction less than 1, then we would have a converging series by the ratio test. So I don't want you to get the idea just because this one turned out to be 0 and this one turned out to be infinity that is either always the case or always necessary, because it is not.